Hello, it's Dumplet here. Here's an item on geometry. We have a semicircle and 5 circles inscribed in the semicircle, as you can see. What fraction of the semicircle is shaded? Now credits to Alim Boss for this item. As usual, pause this video if you'd like to give this item a try, but if you're done, let us dive into the solution. Alright, so we might want to write some lines down, maybe take a look at the radius of the smaller circle, and in a way we can get the larger circle's radius, the semicircle's radius in terms of like the smaller circle's radius. But before that, we're going to make some small assumptions, and we're going to say, without loss of generality, I'm just going to make each of the small 5 circles have a radius of 1, because everything can be scaled up and down. But again, to make our calculations a little bit more simple, without loss of generality, let's just make the small circles have a radius of 1. And let's just call the radius of the semicircle to be r. Alright, so if the circle has if the radius of the smaller circle is 1, we can kind of form like a nice shape here, like a kind of like a house. And you're going to realize that I'm only going to focus on a little bit on the left part of the figure, because everything can be acquired from the left figure, and we're going to make some observations based on the left part of the figure. Alright, so let's try to draw some points so we can call these segments a little bit better. Alright, now first thing to notice is that, let's just say B is the center of the larger circle. Now it should be obvious enough that the middle circle should be tangent to the semicircle at point B, which is the center of the semicircle. And let's just say points A, F, E, D, and C. So C, D, and F, they are the centers of the 3 circles, and we can talk about point E and point A in a while. Now, first thing to notice is that BA is also tangent to this yellow circle with center at F. So AB, or BA, it's going to be perpendicular to FA, hence the right angle here at point A over here. So FAB is right, so AB is the tangent to this circle. Now we're going to come back to this in a while. Now let's talk about these 2 points, which are the tangency points of the yellow circles to the semicircle arc. So we have here this green point, these green points, they should be collinear with F and B and D and B respectively. So if I'm going to call them P and Q, then PFB is collinear and then QDB is collinear. Now since the smaller circles we set to have a radius of 1, technically speaking PB is a radius and QB is also a radius of the semicircle, since B is the center. And we can kind of say that FB and DB, that's going to be equal to the radius of the semicircle, then subtracted by 1. So we're going to subtract PF from PB, and we're going to subtract QD from QB. So we can say that FB and DB, they have lengths of r minus 1. Now this brings us to focus on triangle DFB over here. Now since DB and FB, they're both equal to r minus 1, well, BE, it's a median to DF, because, well, DE and ED and EF, they are both radii of the 2 circles over here, so they both have a length of 1. Since E is the BE over here is the median to DF in an isosceles triangle with FB equals DB, then BE over here must be an angle bisector and an altitude at the same time. So BE would be tangent to FD. Now this gives us pretty nice results, because BE is tangent to DF, which we can say BE is a tangent to circle F. And since we talked about AB being a tangent to circle F, we know that AB and BE must be of the same length, because they both originate from an outside point B, and these 2 are tangents. Alright, now from this we would know that by congruent triangles, angle FAB, let's just call it alpha for now, angle FBA If that's alpha, then angle EBF, this angle over here, must also be alpha. Now, this is pretty interesting because we have an isosceles triangle based on the fact that FB equals DB. So triangle FBD is an isosceles triangle. I talked about BE being a median, which in effect is also an angle bisector. So this angle over here will also be alpha. And that kind of leaves us with angle DCB over here. Let's just call this beta for now. And we're going to go back to beta in a while. But basically, here we have just like an angle DBA being trisected here. So we have 3 bunches of alpha. And we will be able to use this in the next part. All right, so we can have a relationship on sine alpha because we already have the lengths that we kind of need. Sine alpha in triangle FAB. So in triangle FAB, sine alpha, it's going to be opposite, which is 1, over the hypotenuse, which is r minus 1, as you can see here. So sine alpha equals 1 over r minus 1. And here, I'm going to use the triple angle identity for sine. Again, you can easily derive this, or you can just memorize it. It's totally up to you. But I will be able to get that sine 3 alpha, which is going to be 3 sine alpha minus 4 sine cube alpha. And since sine alpha is just this value, I'm just going to substitute it in here. So this will be the value of sine 3 alpha. I'm going to come back to this in a while. And then let's try to focus on triangle DCB. And I'm interested in getting the value of cosine beta. Again, I can use the cosine law to help me here. So DC is technically of length 2 because it's just connected by 2 radii of length 1. So 2 squared is going to be equal to 1 squared plus r minus 1 squared minus 2 times r minus 1 times cosine b, again, just by cosine law. Now, if I solve for cosine b, that's going to give me this value over here. All right, now why did I get sine 3 alpha and cosine b? It is because, recall that we have a right angle on b here. So angle CBA here is right. This tells us that 3 alpha and b, they are complementary, which means they add up to 90 degrees. This tells us that sine 3 alpha must be equal to cosine beta. And that's going to be the equation that we'll be able to form. We'll be able to equate this expression in terms of r and this expression in terms of r. We can solve for r and work on with our solution. So this is the value of sine 3 alpha, and this is the value on the right of cosine beta. They must be equal because of the fact that 3 alpha and beta, they add up to 90 degrees. All right, let's try to solve for r here. Now, I can multiply both sides by r minus 1. We can clear one of the r minus 1 in denominators. I'll get 3 minus 4 over r minus 1 squared. It's going to be equal to r minus 1 squared minus 3. So manipulating the numerator over here to kind of get us an r minus 1 squared. Now I would make the substitution that y is equal to r minus 1 squared to kind of simplify our calculations. If I substitute y, it's just going to be like this. Now it's just a matter of solving for y here. Again, you're just going to clear the denominator, so we'll be able to get this part and then bring everything to one side. So y squared minus 9y plus 8 equals 0. That's nicely factorable. We're going to get y equals 8 and y equals 1 based on the factoring. Now, don't forget that we made the substitution for y. So r minus 1 squared, that's going to be equal to 1 or 8. And let's try to take cases. If this was equal to 1, then we're going to get the possible values of r of 0 and 2. And if we take the case where it's equal to 8, we're going to have the 2 possible values, 1 plus 2 squared root of 2 and 1 minus 2 squared root of 2. Now, that's a lot of values for r. We should be able to get just 1 out of these 4 possible values because there should be only 1 possible value for r. So we kind of have to go back to the figure. Now, obviously r equals 0 is impossible. I'm pretty sure the radius of the semicircle can't be 0. And I'm pretty sure it can't be negative as well. So that just brings us 2 and the 1 plus 2 squared root of 2. But we can easily eliminate the fact that r can be 2. So because of the fact that, well, this is a radius, so that's equal to 1. This is also a radius, so that's going to be equal to 1. Now, r is obviously greater than this one, based from the figure. So I think r is not equal to 2. And that gives us the only possible value of r, and the only logical value of r to be 1 plus 2 squared root of 2. And there we have it. We now have the radius of the semicircle, and since we just made the assumption that the radius of the smaller circles, again without loss of generality, assume it to be 1, we can now get the fraction of the semicircle that is shaded. Now the shaded region is just 5 pi because each of these is just pi r squared, well the r is 1, so all of these 5 small circles, they each have a value of an area of pi, so adding them up gives us 5 pi. And then for the area of the semicircle, it's just simply pi r squared over 2. Now the value of r is going to be the 1 plus 2 squared of 2, so just substitute it into the formula, and we can kind of simplify this out. We can cancel the pi's, and we can multiply the numerator and the denominator by 2, giving us 10 divided by 1 plus 2 squared of 2 quantity squared. Now you guys can work out the algebra here. It's just going to be like the expansion of a plus b squared, and that's going to give us the value of 1 plus 4 square root of 2 plus 8, and that's going to give us 9 plus 4 square root of 2. Now we have a denominator with a radical, so we kind of want to rationalize this. So we can rationalize the result, multiply the numerator and the denominator by the conjugate of 9 plus 4 square root of 2. So we're going to multiply 9 minus 4 square root of 2 in the numerator and the denominator, and then simplify our result. Multiplying 10 and 9 minus 4 square root of 2 gives us 90 minus 40 square root of 2. Pretty simple in the numerator. And in the denominator, it's going to be like an a plus b times a minus b case. That's going to give us a difference of squares, a squared minus b squared, giving us the 81 minus 32. That's going to be equal to 49. So simplify our answer. We're going to get that the ratio, or the part of the semicircle that is shaded, that's going to be equal to 90 minus 40 square root of 2 divided by 49. And this will be our final answer. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye!